Today on Macaulay Math, we're learning the unit circle. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 17 on the unit circle. Our goals for today. We're going to identify a circle and its relationship to the real numbers. We're going to evaluate trigonometric functions using the unit circle. We're going to use the domain and period to evaluate sine and cosine functions, and then we're going to use a calculator to evaluate trigonometric functions. Using the unit circle to evaluate trigonometric functions is much like learning your multiplication tables in elementary school. It provides a ground level understanding of the operation and keeps the mathematician from going to the calculator to perform mundane and often repeated calculations. Memorize the unit circle and put it into long-term memory. It will make your mathematics life much easier in the long run. Let's get started.
Okay, so we're going to start talking about the unit circle, and I'm going to build you a unit circle in class and show you that a lot of the values repeat over the course of the unit circle. And there are some tricks and tips that you can use to help you memorize the unit circle. But the unit circle is based on special right triangles, and you learned special right triangles in geometry. And I know it's been a while, but there were two special right triangles, the 30, 60, 90 right triangle and the 45, 45, 90 right triangle. And there were some proportions that went along with that, and I'm not going to go through building them up. If you would like to, I'll take the time and do it in class. But to keep the video short, I'm going to remind you that this side was x for the 30, 60, 90 right triangle. The hypotenuse was 2x, and then this far side was x square root of 3. And then for 45, 45, 90 right triangle, they called this side x. And because it was an isosceles triangle, this side was also x, and this was x square root of 2. And again, if you'd like to see how we get these proportions, just ask and I'll do it in class. It's fairly easy, and it uses the Pythagorean theorem. Now, when we're talking about the unit circle is a circle of radius 1 unit long. Now, in the unit circle, all of these hypotenuses are going to be of value 1. And so if I make these two sides 1, the other two sides change proportion. And it's fairly easy for us to see the values that we're going to use. But if I make this a 1, and I make this a 1, then this side becomes a half, and this side becomes square root of 3 over 2, and this side becomes square root of 2 over 2, and this side becomes square root of 2 over 2. And so these 4 values become 4 of the 5 values that are on the unit circle. These are the things that you're going to have to memorize. 1, square root of 3 over 2, 1/2, square root of 2 over 2. Now just a couple notes. The unit circle is a circle of radius 1, meaning 1 unit. That means every radius is 1 unit long. These 1 unit radii are hypotenuses of right triangle. And what you end up getting when you do this is a unit circle that looks like this. Now, I am going to hand you, I probably have already done it at the beginning of the unit, a practice unit circle quiz. At some point, you are going to have to memorize all of these values. The good news is that there are a lot of values that are repeated, and there are a lot of patterns in here that are going to make this easy for you to memorize it. Now, this unit circle that I have here is very pretty, but it's not perfect. In your unit circle quiz, you are going to have to know the degree, the radian measure, and the point. There's 1 point for each of these all the way around this circle. Now there's one value that's missing on this unit circle that I need on my quiz, and that is this last value. It is 360 degrees. It is 2 pi radians, and it is back at 1, 0. I don't often make you memorize and regurgitate things for me. This is one of the rare instances. This unit circle will be your math facts that you will be using from now until the end of trig. And we have 3 units of trig. And so you should think about learning the unit circle the same way you learned your times tables back in 3rd grade. If I ask you to do 2 times 5 during the course of a quiz or a test, you don't go and grab your calculator to do 2 times 5. You just do it in your head because you learn the math facts. And that keeps you from having to do a bunch of little tasks to get a bigger task. Learning your unit circle will allow you to do many sine and cosines in your head and do those calculations the same way you do the calculations for 2 times 5 and 10 times 8. All of those things you do in your head. Now, I have never had a student say, wow, I didn't need to memorize the unit circle as well. But I have a lot of kids that when they get to the 3rd unit in trig go, man, I sure wish I would have memorized the unit circle a little bit better than what I have. So please, please, please commit this to your long-term memory. Take some time to learn it. Take some time to learn the patterns. And you're going to see there's a lot of patterns. First, you're going to see that all of the values, all of the points, and when I say points, I'm saying ordered pairs in the XY plane. There are only 5 numbers that you have to memorize. 1, 0, square root of 3 over 2, 1/2, and square root of 2 over 2. Those are the only numbers there. If you look at this square root of 3 over 2 and 1/2. Any radian measure that is something pi over 6 has square root of 3 over 2 for the x and 1/2 for the y, and it just changes signs. So if I look over here, I have 5 pi over 6, square root of 3 over 2, 1/2. 7 pi over 6, square root of 3 over 2, 1/2. 11 pi over 6, square root of 3 over 2, 1/2. The only thing that changes is you have to remember what quadrant the angle is in, and that will tell you which of the 2 points has positives and negatives. In the first quadrant, both the x value and the y value are positive. In the second quadrant, the x value is negative, the y value is positive. In the third quadrant, the x value is negative, the y value is negative. And in the fourth quadrant, the x value is positive and the y value is negative. And again, I will show you how to build this unit circle in class. Probably have already done that by now. Using a trig expression to find y. If you remember from geometry, your SOHCAHTOA mnemonic device. SOHCAHTOA is a mnemonic device to help you remember which trig function to use when solving for a part of a right triangle. When you are talking about sine, you must have an off angle. You must have the opposite side to that angle and the hypotenuse with regards to that angle. When you're talking cosine, you must have the adjacent side to the angle and the hypotenuse. When you're talking about the tangent of an angle, you must know the opposite side and the adjacent side. Now, with that, when we're talking about the unit circle, all of the hypotenuses have a length of 1. And for sine and cosine, when you have 1 in the denominator, it becomes just that opposite side. If I'm thinking about the values in this triangle, this side here is my opposite side. This side here is my hypotenuse. And so if I set it up, sine of theta equals opposite over hypotenuse, the sine of theta is equal to y over 1. Now, y divided by 1 is just y. So when you're using the unit circle, and again, this is why you are memorizing it, because in the unit circle, if I know what theta is, I go to that angle measure on the unit circle, and the y value is the result of that trig function. So, as a for instance, this is a simple instance. If I say, what is the sine of pi over 4? Well, let's go back to that picture of the unit circle. pi over 4 is right here. The y value is square root of 2 over 2. So the sine of pi over 4 is square root of 2 over 2. And that is your answer. Using that, we can further extrapolate expressions for all of the trig functions. We just showed that the sine of theta, the opposite over hypotenuse, would be the y value over 1, which would reduce down to y. The cosine, the adjacent over the hypotenuse, the adjacent side is always going to be the x value. The hypotenuse is always going to be 1. So the cosine will be just the x value. The tangent is the ratio of the sine to the cosine. And since the sine of theta was y, we just plugged in y. Since the cosine of theta was x, we just plug in x. So the tangent is the ratio of the y value to the x value. The cosecant, the secant, and the cotangent are just the reciprocals of the sine, the cosine, and the tangent values. A couple of examples. So if I say, what is the sine of pi over 2? What that literally tells me is what is the y value on the unit circle when theta is pi over 2. So I go back to this unit circle, and again, you want to memorize this so that you can do all of these in your head. There is pi over 2 radians, the y value is 1, come back to here, and I say this is just 1. The cosine of 3 pi over 4, that says what is the x value on the unit circle when theta is 3 pi over 4. So I go back to the unit circle. I start at 0. I go to 3 pi over 4. I want to know what the x value is. It's negative square root of 2 over 2. Come back here. This is negative square root of 2 over 2. Last example on this page. Says, what is the ratio of y to x on the unit circle when theta equals negative pi over 3. Now, negative pi over 3 means that we are going clockwise on the unit circle. So if I start here, negative pi over 3 will be 5 pi over 3. Now, tangent is the ratio of y to x. So I have negative square root of 3 over 2 over half. So I'll come back up here, negative square root of 3 over 2 all over 1/2. We should reduce our fractions. This one's pretty simple. I go negative square root of 3 over 2 times, when you divide fractions, you take the reciprocal of the bottom and you multiply by the numerator. So I'll have 2 over 1. My 2's cancel. I get negative square root of 3 over 1. We would never leave an answer like that and just say that this is negative square root of 3. Final answer. Next, periodic function. A periodic function, f, is periodic if there exists a real number c such that f of t plus c is equal to f of c for all t in the domain of f. The smallest number, c, for which f is periodic is called the period of f. Now, that's a lot of words, and I understand that, but it's actually pretty simple. So let's go to Desmos, and let's take a look at an example. And so here I have f of x equals sine x. And we can relate that to just that f of t, we're going to say. And I want to go, and let's say I do another value, and I say sine of x plus some constant a. We'll put a parenthesis around there. And you can see when a is 1, I have this repeat. So I need to find a value for a that makes these two functions line up. That's all that this says. I need a value for c that makes these two functions equal to each other. Well, if I move this slider over, and remember, when you're doing plus a constant, and that's all I'm doing, remember the transformations.
We're translating left a units.
If I move this over, look at me moving it over, look at me moving it over. I get pretty close right there. 6.3. What is that about? And you can see it's not perfect. Well, 6.3, that's pretty close to 2 pi.
And when it's 2 pi, all the points in f line up with all the points in g.
F of x and g of x are equal.
Now there are multiple values for a that will make these two functions line up. But the smallest value that makes them line up is the period. And in this case, the period of sine x is 2 pi.
Even odd trigonometric functions. I know in Algebra 2 we talked about even and odd functions, and they're a little bit different. An even function is symmetric about the y-axis, and odd function is symmetric about the origin. And we know that if you look at sine by itself, it is symmetric about the origin. And what I mean by symmetric about the origin is for any x, y value, there's also negative x, negative y. So pi over 2, 1 has a corresponding point, negative pi over 2, negative 1. And you can do that for any point on sine. And all this is saying is that if I had sine of negative x, that would be equal to the negative sine of x. And that's simple to show. I can go sine of negative x, and we see that that was a reflection about the y-axis. And if I type in g of x is equal to negative sine x,
the two functions line up and become equal.
And you can do that
For any of these identities.
if I do cosine. Cosine of negative x, that is going to be equal to just the cosine of x. And again, the reason that that is true is because cosine is an even function. If you reflect about the y-axis, which is what we're doing in this top function, you will get the original function back.
And you can do a similar demonstration for all 6 of these identities.
All right, last example. It says find the 6 trigonometric values for the given real number angle. So if this is theta, I can say that I need to find the sine of theta, the cosine of theta, the tangent of theta, the cosecant of theta, the secant of theta, and the cotangent of theta. Now, since theta is 5 pi over 6, if I go to the unit circle and I come over here to 5 pi over 6, the sine is the y value. So I have a half here. We'll go back to the example and we'll say that that is a half. The cosine at 5 pi over 6 is negative square root of 3 over 2. So I will go back and say negative square root of 3 over 2. And then the tangent will be the y over the x. So in this case, I get a half over negative square root of 3 over 2. And when I do that reciprocal, I unfortunately get 1 over negative square root of 3, which I need to rationalize the denominator. So square root of 3 over square root of 3, just multiplying by 1. That gives me a final answer of negative square root of 3 over 3. 1 times square root of 3 is square root of 3. Negative square root of 3 times square root of 3 is negative 3. I move the negative up. That's my final answer. Now, these remaining trig functions are just the reciprocals of these values. Flipping over a half becomes 2. That's easy. Flipping over square root of 3 over 2, I will get negative 2 over square root of 3. And again, you can't leave a radical in the denominator. So we'll multiply by the funky 1, square root of 3 over square root of 3. That gives me negative 2 square root of 3. And then square root of 3 times square root of 3 is just 3. That can't be reduced. The reciprocal for cotangent would be the reciprocal of square root of 3 over 3. That puts that square root back on the bottom. But I know that 1 over negative square root of 3 is equal to negative square root of 3 over 3. It just was improper. So I'm going to flip this fraction and make it negative square root of 3 over 1 and just say that's negative square root of 3 and be done with that. So that's an answer. That is an answer. That is a solution. That one, and that one. Okay, last example. Find the sine of 13 pi over 4. Now clearly 13 pi over 4 is not on the unit circle. 7 pi over 4 is the largest one that's actually pi over 4. 8 pi over 4, which is going to be important in a second, is the same as 2 pi. And so clearly that is not on the unit circle. So the way you want to think about it in terms of the unit circle is 13 pi over 4 is starting here and it keeps going around until we get to 13 pi over 4. That means 13 pi over 4 is going to have a coterminal angle that is on the unit circle. So the way that we're going to find that coterminal angle is we are just going to take that 13 pi over 4 and subtract multiples of 2 pi away from it until we get something on the unit circle. Now this one's pretty easy. 13 pi over 4, subtract, I need to change 2 pi into fourths, and I'll still have the pi there. So how many fourths are in 2? So if I took 2 units and I divided those all into quarters, I would have 8 quarters. 13 pi over 4 minus 8 pi over 4 is 5 pi over 4. So since 5 pi over 4 is on the unit circle, the sine of 13 pi over 4, and remember 5 pi over 4. So if I want to draw this accurately here, I go all the way around once and then I go to here, and this would have the same value as if I went from the unit circle and just stopped right there. So 5 pi over 4 equal to the sine of 5 pi over 4. And here, since this is on the unit circle, it says find the y value at 5 pi over 4. I go to 5 pi over 4 on the unit circle, and I see that that is negative square root of 2 over 2. That doesn't reduce. So this final answer is negative square root of 2 over 2. All right. That is all I've got for today, folks. So, the Star Wars fun fact of the day. Splinter of the Mind's Eye is a non-canon novel, first published in 1978. Originally, the story was written as a fallback plan for a cheaper film sequel to A New Hope, which was released in 1976, had Star Wars not been the success it was. As we all know, Star Wars is a cultural phenomenon. It was back then in 1976, and it made so much money that he could do the full-blown version of The Empire Strikes Back, which is easily the best Star Wars movie ever. So says Mr. McCully. Well, that's all I got for today, folks. Have a great day. Goodbye.